All right, so symmetry of a graph. We're going to look at 3 symmetries, and then we're going to forget about one of the symmetries. And the question I'm going to ask you eventually is, why are we forgetting one of the symmetries? Okay, so we'll start with this one. Y-axis symmetry, meaning it's reflective over the y-axis. What's on the left side of the y-axis exactly matches the right side of the y-axis. Graphically speaking, people normally don't have any problems with this. You can tell if you fold it along the y-axis and it matches up, it's symmetric. The problem comes about when I ask you to prove it algebraically. And the process that you use for that, and I'll take you through a couple examples, is you're going to plug negative x in for x. Simplify things and see if it matches what you started with. It'll make more sense when we go through the example, and I know you've done this before, right? Okay, good. Some of you shake your head, some of you look like I'm speaking Italian. So, red is a summary. Plug negative x in for x and check to make sure that the equations are the same. This, by the way, is what's also called an even function. So, 3 things. Number 1, check it algebraically. That's the hardest part. Number 2, look at the graph and see if it's symmetric about the y-axis, which is fairly easy to recognize. The other thing is you can cheat a little bit. If your function is a polynomial, if all the exponents are even, then that function would be even. For instance, x squared. X to the 4th plus 2x squared would be an even function. Remember that x is x raised to the 1st. What about 7? What about the function x squared plus 7? Would that be symmetric about the x-axis?
No, because it's raised up some.
Wait, is it magic?
Yeah.
Yeah.
It's no because it's raised up some units. Yes.
You have a true answer and a false answer. So yes, did you say yes it is symmetric?
Yeah.
And why does being, so I guess you have 2 correct answers. Yeah, but, so the
I think
7 means it just shifted
Yeah.
up 7 units, so it doesn't shift left or right.
Yeah.
Perfect. Why else is it symmetric about the x-axis? Tell me about the number 7. What's the exponent on the x for 7? Does that seem like a dumb question?
0.
It's 0, correct. So x, 3x is x raised to the 1st power. 7 is 7x to the 0 power. But of course it would be silly to write 7x to the 0 power. X is even, or sorry, 0 is even, so it still counts as a symmetry about the y-axis. Okay, we good on that? And again, I'll take you through some examples when we get done talking about all of them. Second one is reflective or symmetric about the x-axis. Process is the same, we just look at the different variable. Instead of plugging negative x in for x, we plug negative y in for y. And then again, check to make sure that they are equivalent expressions. And then the last one is symmetric about the origin. Now the y-axis symmetry and the x-axis symmetry are easy to tell graphically. Origin symmetric is a little bit more difficult. The secret there is take your calculator and turn it upside down. Does it look the same right side up as upside down? Then it would be symmetric about the origin. Okay, so if I could pick up the board and spin this puppy around, it would match. We good? That's called an odd function because all the exponents are odd. X cubed plus x. There are 3 different symmetries that I just gave you. Which one are we going to forget about? Origin? X-axis. Anyway, I don't know y-axis, so we can cover all 3. For those of you that said origin, why origin?
Because it's symmetrical to the x and y axis, it's symmetrical to the origin.
If it's symmetrical to the x-axis and y-axis, then it's symmetrical to the origin, so we forget about origin and just look at x and y.
Yeah.
Sounds real good, not correct. Good guess. For those of you that said x-axis, why x-axis?
Because if it's symmetric on the x-axis, it's not a function.
Beautiful. Function, we're okay. Not function, bad. We deal with functions in here. Function, good. Okay. So we will eventually blow off step 2. We're not going to care about x-axis symmetry. All right, we good? All right, let's see what that looks like algebraically. There's a nice summary chart. That's in your book if you want to copy it down later. You'll see a lot of times I'm going to give you, if we go back to this slide for instance, I'm going to give you two chunks of information on a lot of slides. One is what I call the calculus speak. It's the artsy-fartsy fancy theorem. The other one is something in a little bit more plain English. You have to decide what of this you want to write down. You want to write down all of it, that's good. You'll probably have a hard time keeping up. You want to write down just the red, that's good too. You want to write down just the black, I don't care. Whatever's going to help you. Okay, so let's take a look at this one. If you just look at the function before we do any work with it, what can you tell me? Why?
Because they're all odd.
Beautiful. All the exponents are odd. We've got 3 and 1, therefore it should be symmetric to the origin. What about y-axis? No. Is it possible to be symmetric about the origin and the y-axis? All right, let's think about that for a little while. All right, so a couple things. Number one, Kit looked at the exponents and said, okay, those are both odd. It's an odd function, symmetric about the origin. Bingo, that's the first thing. Second thing, you could graph it. It's in the form of y equals, slap it in your calculator, what will it look like? Everybody does this, I love that. Yeah, it'll look like this. And this looks really, really good on the video too. Yeah, it'll be a cubic. It's got the little valley and hill. Question?
So if the exponents are both odd, they are symmetric about the origin.
Correct.
So what happens if they're both even?
Then it's symmetric about the y-axis. And what if you have even and odd combined? It's neither. Just some weird function that's not going to be symmetric at all. That's the easy stuff. Now the hard part, we need to verify it algebraically. So it goes something like this. You start with your original function and you plug in negative x for x. And then you simplify. What's negative x quantity cubed? Negative x cubed. What's the opposite of negative x? In other words, what's this when you simplify it? Positive x. So when you simplify that expression, you get down to that. Does that match the original function? No. Now you may have to look at a couple things, like you may have to factor out a negative sign to see if you can get it to match. If you have negative signs on both sides, you may have to manipulate a little bit, but that's pretty obvious that the first step and the third step don't match. Therefore, it is not y-axis symmetric. Done. And that's how you verify it algebraically. We've also cheated a little bit that we know what we're going to get for an answer anyways. We knew that this wasn't going to work because of the other techniques. We also know that the next one is going to work. So plug in negative x and negative y for the origin. Simplify. Well, we know what the right side's going to be. We did that already. That's going to simplify down to that. The left side, however, does not match what we started with. So what do I do next? Go ahead.
Divide by -1.
Divide by -1. Okay. So you multiply or divide either one. Divide by -1 on both sides. The left side becomes y. The right side becomes 2x cubed minus x, which matches where we started, and therefore, as we already determined, it has origin symmetry. It looks the same right side up as upside down. Okay, we solid? Should be a review, yes? I wasn't really expecting an astounding yay, but that's okay. We talked about this already, could have graphed it. That's what it looks like. So again, you see that it doesn't fold across the y-axis, but if I pick this up and turn it over, it'll match exactly. So it fits what we already planned. I would like to say you're just going to always have your calculator and be able to graph a function, look at symmetry graphically and turn it over and stuff. That's not always going to be the case. You're going to see instances where you do have to verify it algebraically. Plug in negative x, plug in negative y, or plug in both negative x and negative y, and simplify that bad boy. Okay, we good with this? Good, that finishes day 1. Any questions? All right, beautiful. Let's move on to day 2 then.
Did you see you post these?
End of the day. So one of the things we'll have to get comfortable with as we work through this stuff is the pace of the lesson. So if I'm going way too fast and everybody is all getting blown out of their chair, then just raise your hand and ask me to go back a slide. But if everybody's okay and you're the only one behind, then you either got to pick it up, meaning write down less stuff, or you can go back and make use of these later. So again, it's a matter of what you want to do. That reminds me of another thing about the homework. I think I talked about this yesterday, but I'm not sure. You're also going to have to walk that thin line between where do you come into class, if you have problems on homework, when do you come into class, or when do you seek help before you come to class? Did I talk about that yesterday?
No.
Okay, so if there's, let's say, 10 homework problems, and you miss 1 or 2 of them, that's fine, come into class and ask some questions. But if there's 10 homework problems and you could only do 2 of them, you may need to come and see me before class to get some clarification on that stuff before you get into class. We won't have time in class to go over every single homework problem. We'll come back to that tomorrow. All right, coming back to graphs, points of intersection. So yesterday we talked about x-intercepts and y-intercepts, which are an easy approach, where you're determining, again, where that function crosses the x-axis or crosses the y-axis. How does that differ for points of intersection? Now we're going to take 2 functions and have them intersect and figure out where that happens. It could be 2 functions, could be 3. Most of the time we're going to do 2 functions. So we'll start with these 2. Let's look at this first function. What can you tell me about that function?
It's a quadratic.
It's a quadratic. Okay. And how about this guy?
Linear.
It's linear. How many different ways can a line and a parabola intersect? Taylor?
2 max.
2 max. Tell me about them.
Well, like, the line can go through both ends of the parabola.
Okay.
Yeah.
That's it. That would be 1 way. So 2 points of intersection, 1 possibility.
No, I mean, there's infinite, right?
I don't know.
There's only 1 because the line is just 1 line.
Tell me your name again.
Mason.
Mason.
Another possibility would be with the vertex, so it would be only 1.
So 1 possibility. Oh, so now 2 possibilities, 1 intersection. So we can have a line intersect. I'm just repeating what you guys are saying to make sure I understand. So you're saying we could have a parabola intersect a line in only 1 point. If it goes like straight down, it hits the vertex. Or anywhere. I mean, if you intersect a standard parabola with a vertical line. Where did I put my pen? Losing my stuff. Okay, so you're talking about something like that. Right?
Yeah.
Okay, and Taylor, you were talking about something like that.
Yeah.
Okay, whoops, arrowheads, not points. 1 point of intersection, 2 points of intersection, 2 possibilities, is that it?
No.
No?
What if you have a parabola with just a line at the bottom?
A parabola, what kind of line?
One top. No, like on the, yeah, there.
How many points of intersection? 1. So that still fits in with this, right?
Yeah.
Ooh, look at that. What about the original one I drew? 0. So 3 possibilities. So solving this problem, you need to be aware of the fact that if we're intersecting a parabola with a line, we have 3 possible outcomes. You could get some weird funky answers that don't work, meaning they don't intersect. You could get only 1 possibility, or you could get 2 possibilities. Any guesses and or ideas how many we're going to get on this one? 2? Standard intersection, let's see. Well, there's the picture, so we know our answer right away. And now we're going to verify that with the math. Notice it's a standard, basically what Taylor outlined for us earlier. We have a line going through a parabola that hits in 2 points. Great. Graphically, no problem. Algebraically, how do I find those points of intersection? Set them equal to each other. Meaning what?
If you isolate the y,
John?
if you isolate the y variable, then you can set the equations equal to each other. And you can solve for x and find the x value of the point, and then find the y value of the point by plugging that in.
Perfect. And I believe I did that. So solve both of them for y, set them equal, and then solve. What do I do next from this point?
Move it to one side.
Yeah, move everything to
Set
one
equal
side.
to 0.
Set equal to 0. Did that, got a nice little quadratic. Now you have a choice. You could factor that, which it does factor nicely. You could plug it into your calculator. Is it safe to assume you all have the quadratic formula on your calculator? Does anybody not? All right, we'll have to get that to you guys as soon as possible. This is way ahead of the game, but the AP test has 4 parts to it. There's show your work, calculator, show your work, non-calculator, multiple choice calculator, multiple choice non-calculator. So you're gonna have to be very adept at using your calculator. You're also gonna have to be very adept at not using your calculator. Most of the time, a problem like this would probably show up on the calculator portion because they don't really challenge you that much on factoring quadratics. But I think at this stage, you should all be able to factor that into its 2 values. Find the 2 x's, and then John, what was the last step you said to do? What do I do with those x's?
You plug them into one of the original equations.
Doesn't matter which one.
It doesn't, but it seems like the linear one would be easiest.
Well said. Take those 2 numbers, plug them back into one of the equations. It doesn't matter which one. And as John said, I would probably use the linear because it's a little bit easier. 2 minus 1 is 1, and negative 1 minus 1 is negative 2. Because we're looking for points of intersection. Common mistake that people make on the AP test is a problem like this pops up. They find the x values and then you stop. And unfortunately, when that happens, you get no points for that. Because they're looking for points of intersection, so they want an x value and a y value. Which gets us that. Okay, we solid with that? Good. And that's going to change depending on the function. Let's suppose we intersect a cubic with a line. Now the number of possibilities increase. We could get 3 intersections. Could you get 2 intersections? You could get 2 intersections. Could you get 1? You could get 1, and you could get 0. So now all of a sudden we have 4. So that'll be fun. The mother functions. Do you know the mother functions? What are they? Do you know the term? Have you never heard that before? Yeah, you have. What are they? These are, by the way, I'll tell you what they are. You're going to tell me what, then you'll tell that made no sense. Mother functions are functions that are basic functions that you absolutely have to know how to graph, what they look like, and how they work. What are they?
Y equals X.
How's it okay?
Y equals X.
Okay, linear term, linear equation, right? Y equals mx plus b, y equals x, whatever line you want to use. What do you got?
An absolute value one, y equals absolute value next, that one.
That would work. It's further down, and I can't click to it next because that would have been really, well, which one would be logically next? A quadratic would be next, but a cubic is also on there. After a cubic, we go to quartic. You don't need, that's not a mother function. We will work with quartics and quintics. I think we stop at quintics. I don't remember what's next, so I'll just click. Absolute value. That worked out well. Any others?
Square root.
Lucas?
Logarithmic?
Logarithmic? Do we work with logarithmic? I don't think we do. And I'm pretty sure it's not on my list.
Squares.
I'm sorry?
Squares.
Squares. Square roots. Squares are under quadratics.
Oh, yes.
Square roots are close to semicircles. So are exponentials. They're square roots. Okay. Semicircles, not circles. Why not circles? It's not a function. So if we chop it in half, all of a sudden we got a function. We'll deal with top semicircle, bottom semicircle, and sometimes we'll even be feeling saucy and we might work with the left and right even though they're not functions. Exponential, what's that look like? Good, that. Okay. The spread of the zombie apocalypse, exponential. One zombie kills one person, that person becomes a zombie, kills 2 people, those 2 people kill 2 people, and then next thing you know, The Walking Dead. Square root, what's that look like? Right. Not the bottom half, it's not a sideways parabola, it's just the top half. Okay. And we'll do a bunch of work with mother functions. You need to know how to graph each one of these. Some of them might need a review. You might need a little review on graphing the absolute value. What's the absolute value look like? Yeah, it's the V. Okay, or the check mark. Got that, square root, we're good to go. So you should know all of these, right? Good. We're done. So day 2 was a lot quicker. All right. Let's go back, since we have a couple minutes, let's go back and talk about semicircles. So our standard form for a semicircle, our standard form for a circle is what? What's the equation of a circle?
X squared plus y squared.
Equals r squared. So let's make our radius 4. Okay, so that's the equation of a circle. What can you tell me about that circle? There's 2 things you're concerned about with a circle. Maciek.
It revolves around the origin. Well, like, the
Yeah,
center
that's
is the
fine.
origin.
Yeah, the center's at the origin, and
Has a y value of 2 and the x value
can you say that in a different way?
2. It goes up 2 units and then 2.
Good.
Radius of 2.
There you go, radius of 2. It has a radius of 2. Standard form actually is x minus h quantity squared plus, whoops, that's supposed to be a y. Y minus k squared equals r squared. Okay, so let's start with that circle, not a function. We want to turn it into a function. So in order to turn it into a function, I want to solve for y. So y squared is equal to 4 minus x squared. Take the square root of it. Pop quiz. What did I just do wrong? Plus or minus. Very good. Take the square root, you get 2 possibilities. Now the nice thing about that is one of those possibilities will be the top half, one of those will be the bottom half. Which is which? Is?
Is it that?
Yep. Okay. So this guy, let's say that's a radius of r, is y equals r squared minus x squared, square root of that whole thing. That's the top. There's the bottom. And those are functions, so we will use those quite a bit. Just for giggles, how would you do the left and right?
The same thing, but solve for x instead of y.
Perfect. And you would get a plus and minus. Which do you think would be which?
Plus would be right.
Good. Okay, so even though it's not a function, we'll still list it here. If we're talking about the right-hand side, that would be x is equal to the square root of y squared minus r squared. Oh, no, I did that wrong. It's backwards. R squared minus y squared. And that would be the right side. And then, running out of room here. Over here. Can you see that green? A little bit. How about in the back? You probably can't see it because it's too low on the board, right? Should I just avoid using the green altogether?
Yeah.
Okay, all right, in the future I won't use it. Okay, so those are semicircles. Let's move over here. And then square root, just so we're all on the same page. Wow, that's supposed to be a smoother curve, but you get the idea. Square root. Y is equal to the square root of x. Suppose I want to graph the whole parabola, that's the whole sideways parabola. I want the equation of this thing that's not a function that looks like that. What's the equation of that graph?
X equals y squared.
Good. But I want to graph this on my calculator, and I can't graph that on my calculator, Luke. How do I graph that picture on my calculator?
You could do y equals the square root of x, although you have to specify plus and minus, right? This would be-
How do you specify the plus or minus on your calculator? Mason?
Y equals x to the 1 half.
No, because that'll only graph the top part. Matt?
Just graph y equals square root of x and y equals negative square root of x.
Bingo. So y1 would be square root of x, y2. You have to do it separately because the calculator doesn't like non-functions. So you kind of cheated there. Square root, exponential. Exponential. Before I draw it, tell me about an exponential graph. What do I need to know to draw the graph of an exponential? Let's say the basic mother function exponential. I'm sorry?
The power of
What power? What power would you like it to be?
it. Fifth. X to the fifth.
Okay, Taylor?
Isn't like the equation y is equal to n to the x?
Okay. And what's true about all basic mother functions for exponentials? What point do they pass through? Nope. 1 is not a point. 0, 1. Good. Mother function for exponentials pass through the point 0, 1. And then they climb drastically. I think we're good to go with everything else. I think I've succeeded in beating a dead horse. Are we good on this? Okay, beautiful. Anybody know what time this period's over? 40. Okay, so that, instead of going over homework, let's save that for tomorrow. And we're good to go. Okay. So you got about 12 minutes to start knocking out the rest of the homework. You have to finish day 1 from yesterday, which is probably about 5 or 6 problems, and then day 2. We'll go over both of those days tomorrow before we proceed to day 3.